เกิดอะไรขึ้นปุ๊บมาครับ
ผมกดอัดต่อแล้วนะ
ตามไป
ในแอปผมเปลี่ยนเป็นล็อกไม่เป็นนะมันมีเราเปลี่ยนจากล็อกไม่ได้
ไม่เป็นไรครับช่างมันไม่ใช่ทางวินนี่อ๋ออยู่นี่อันนั้นเป็นคุณโยวินเมื่อไรจะหายก็ไม่ทราบครับว่าอันนี้นะครับอันวินนะครับแล้วก็คุณระวังตัวหน่อยนะผมไม่แคปเจอร์คำพูดเขาละเดี๋ยวเขาจะหาว่ามีปัญหากันแคปเจอร์คำในไลน์อะไรก็แต่เขาบอกว่าคนไหนเขาให้ผมส่งรายชื่อนะคนไหนเข้าเรียนไม่ถึง 80% นะครับถ้าพวกทำกิจกรรมของโรงเรียนไม่เป็นไรแต่ถ้าคุณลาส่วนตัวแล้วป่วยอย่างเงี้ยแล้วคุณไม่มีใบรับรองแพทย์เขาจะเรียกคุณไปนะแต่ผมต้องรายงานเขานะครับสิ้นเดือนนี้นะครับคุณก็ระวังเรื่องอันนี้หน่อยนะฟาสต์แดนซ์เนี่ยนะครับของคุณอ่ะเช็คแล้วคุณก็หนีไปกลับบ้านก่อนกันเลยผมไม่ว่าอะไรแต่ว่าคุณทำให้รอดนะสำหรับพวกหน่วยงาน EP ของเวลาเขาจะเช็คคุณนะผมแค่ทำตามที่เขาล็อกของครับนัทวัฒน์ครับไม่มีแจ้งในอะไรนะกูเบนอะไรเขาก็ไม่เห็นแจ้งผมเลยก็เดี๋ยวเดี๋ยวกลายเป็นขาดเย็นนี้นะครับเป็นแอปเซนต์นะครับธนากรอยู่นี่นะครับแล้วก็ทักนะครับที่ทำโทรศัพท์ให้อยู่นะครับแล้วก็ศิลภพจะอยู่แถวๆนี้ไปอยู่นู่นแล้วครับแล้วก็อนิวัฒน์ย้ายมาในโครงการนะโรจน์ระวีเห็นอยู่นะ101โอเคสหรัฐคุณสอบอะไรนะของอเมริกาอะไรเรียบร้อยแล้วหรือยังต้องอีกรอบหนึ่งใช่ป่ะซ้ำให้คะแนนมันมากขึ้นนะครับเอาให้ได้ครับสหรัฐแล้วก็สมาร์ทครับเห็นอยู่นะครับจีโน่ครับนั่งนี่นะครับแดนฟ้านะครับเชียร์กรเดนิสเห็นเต็มฟุตบอลอยู่สนามฟุตบอลยังไม่ขึ้นมาแบบนั้นอยู่โอเคคุณยวีเห็นอยู่นะครับตะกี้นี้นอนอยู่นะนอนเล่นโทรศัพท์สบายๆนะภูมินันท์นะครับสัปดาห์นี้คุณไม่มีลางอะไรไปไหนเลยโรงเรียนไม่ดีแล้วก็ก่อนนอนนะกรรมการนักเรียนนะเดี๋ยวก็ไปอีกกันเองนะครับกันเองโอเคแล้วก็ปิดเคครับปิดเคนี่สุดยอดมากเพื่อนนั่งดิสเล่นกีตาร์ตัวเองนั่งหลับได้ด้วยดูข้างๆเลยคุณแยกส่วนประสาทได้ดีมากไปอย่างนี้ไปอยู่หอนอนหออะไรใครได้สบายง่วงครับวัยกำลังกินกำลังนอนครับโตอันนี้คนเนี้ยผมห่วงมากเลยเนี่ยนัทธนนท์แซดแน่นอนผมเห็นแซดมาจะ2 เดือนแล้วมั้งเนี่ยคนเนี้ยแล้วเขาถ่ายรูปมานะจะมีผู้หญิงนั่งเรียนด้วยเสมอเอ้าคุณก็ไปดูในนั้นดิดูในคลาสในเทนเน็ตทุกครั้งอ่ะคุณก็ไปเช็คดิมันจะมีมือผู้หญิงอะไรอยู่ข้างๆเสมอเลยวันนั้นมีกำลังใจไปเรียนด้วยนะครับเห็นไหมส่วนไม่มีกำลังใจไม่ค่อยอยากมาทักษิณนะครับทักษิณครับผมปัดทำกลับมาแล้วยังปัดทำขอลา2 วันใช่ป่ะ24ด้วยนะครับปิดดีครับปิดประมาณผมคุณากรของเราแล้วก็ธนาธรครับนาริศอยู่นี่นะครับไม่เป็นไรเขาอยู่ในภวังค์ของเขาอยู่แล้วก็กัสซิเดชครับโอเคครับพัฒนนท์ครับ โอเค นี้ที่ตอบคำถามได้แปลกแนวเลยนะแอปเซนเลยนะ ไม่ลงไม่ลาอะไรก็ขาดไปครับภูเมฆครับผมภูเมฆเขาตั้งวงอะไรของเขาเนี่ยเดี๋ยววิบูลย์นั่งหลังไปไหนแล้ววิบูลย์อยู่ห้องนู้นห้องนี้นี่ไม่ได้ตัวเด็ดๆทั้งนั้นเลยผมต้องโอ้โหคาแรคเตอร์แต่ละคนโอเคเยี่ยมมากครับOkay, let's continue our lecture on atomic physics. สวัสดีครับเอาผมมาพอดีผมเพิ่งใส่เครื่องหมายคำถามคุณเมื่อกี้เนี่ยว่าสรุปเอาเนี่ยนะครับห้องนี้นะคุณระวังตัวนะครับห้องเรียนไม่ถึง 80% นะคนที่เป็นแบบนี้นะครับเดี๋ยวดร.เฟิร์สเขาจะเรียกนัทนนท์นั่นแหละผมไม่รู้เขาจะให้หรือเปล่านะนัทนนท์นี่ตัวหายเลยหายไป 2 เดือน 3 เดือนละเข้ามาเรียนครั้งแรกของเทอมนะครับจะไปใช่ไหมแต่ว่ามันยังมาเข้าแถวตอนเช้าอะไรโรงเรียนได้สบายอยู่เข้าแถวเขาไม่มาด้วยสุดยอดมากอาจจะบ้างไกลนะครับเขาเริ่มบ่ายโมงนะเขาก็แบบมาสวัสดีครับตามสบายครับผมก็เช็คให้ตามอีพัสขอต้องการนะครับแต่ว่าผมก็เข้าใจนะคุณก็อายุม.6 ไปแล้วนะคุณก็ยังมีกิจกรรมอะไรอย่างครับตามสบายครับตามสบายครับ
มาไปไหนครับมาไปไหนเขาบอกเลยกินกินไปไหนกินไปไหนเพื่อนไปไหนไอเบส
ไปอ่านดูดิกต
Okay, the negative side in 25 means the kinetic energy is smaller, okay, in magnitude than the potential energy. So when you combine the kinetic energy and the potential energy, you're gonna get something that is negative right here. And once you substitute all the constants, the mass of the electron charge value, the principal quantum number n, and the Planck constant, right, which is h, you're gonna get, you will end up with a simple number. It's not so accurate, okay? Actually, there are some more digits after the decimal point, but for simplicity, like us here in the high school level, we're gonna write only the first digit after the decimal point, which is only 15.6. Okay, but the important feature is the quantum number n. Okay, that still appear here with the power of 2 qubit square. Of course, as I mentioned earlier, the energy turns to be negative. Okay. And in order to better handle we change the energy unit from joule to electron volt, okay, EV, with respect to the electron charge, right? So 13.6 is an important number. You need to remember or memorize yourself. The electron is completely from the hydrogen atom with number 8, the principal number in quantum is very large. So that orbit is very far away from the nucleus. So the distance n index will tend to infinity. Of course, when your n turns to be a large value, this one has the probability. It's going to be even more significant. So when you divide something, whether it's positive or negative, you're gonna get something very close to zero. Even if it's minus of something which is very close to zero, finally you will end up with zero, okay, when n is very large. And the difference between the closest orbit and the distance at infinity, you're gonna get E infinity minus this one, and n is equal to 1. You're gonna get 1. And you're gonna get 0 minus 13.6, and this is 1, right? So it's going to be positive now. So the difference between the electron energy level is 13.6 approximately, okay? Because we get this one of the approximation in equation 27. This is known as the ionization energy of the hydrogen atom. It means you make that atom to be an ion, right? So it means you throw away completely the electron, so you don't have electrons. It means the electron orbit is at infinity. The third assumption by Bohr leads to the wavelength of the EM radiation. It means the energy you get on the left hand side can be derived, can be transformed the energy from the photon, which is related to the Planck's formula, right? E equal to hf. Okay, and whatever frequency that you obtain from the light, from the photon, is going to be multiplied with the Planck constant, and finally you get the energy right here. And because you start from a shell number and a principal quantum number to another quantum number, that the difference will be initial, right, minus E final, because this is the released energy. You're gonna have initial minus final, right? Like this. E initial minus E final. That's derived from equation 15. Okay. But each of energy value should be derived from this formula. Okay. Initial and final. Okay. Ni means the quantum number of the initial state, and NF is the quantum number of the final state, and Ni should be greater than NF, okay, because you jump from a high energy level to the level that is lower, so this will release the energy in terms of photon. Of course, and if you want to have it, of course, you have the common number, which is 13.6. You can move it out of both terms, and you get 1 by NF squared minus 1 NI squared. If you want to see some relation to the wavelength of that photon or the light, you're gonna need to use C equal to lambda f, okay, and f will be C by lambda. When you know f is C by lambda, you can substitute right here on the left hand side, and yeah, the right hand side will remain the same, 13.6, and 1 by f minus 1 by 9 squared. A guy whose name is Rydberg, he is from Sweden, he's Swedish. Just follow this way, and he substitute the value of c, the speed of the light, the vector, on the air, which is really close to each other, and h is the time constant. To the right hand side, okay, h will appear as the denominator, and c will also appear as the denominator. The constant here is defined by him, and it turns out to be 1.09 times 10 to 7. Unit is 1 by 8. And because this is 1 by 11. And this constant will be dedicated to him individually, because he is the first guy who developed this formula. The life of Rydberg is quite interesting. He was a guy who is good at mathematics and physics, and during his time working as a professor at the university, he worked also at the bank. Okay, he used mathematics to solve the problem in bank business. This constant is known Rydberg. The expression here is known as Rydberg formula. It's derived from the very simple relation like this. Okay, now we're going to use the Rydberg constant in the next example at the state n equal to 2. Okay, all of this formula, this one, 30 or 31, is valid for only the atom of hydrogen, which has only a single electron or single proton. If you want to deal with something greater than this, you have to use a modified version of 31. At state n equal to 2, the hydrogen atom would have some questions like this. What is the kinetic energy and potential energy and the total energy? Of course, kinetic energy is 1 by 8. That's positive, right? Potential energy is negative. Right here. Yeah. That's 13%. Potential energy is UA. That's the negative value. And once you substitute everything, you're going to get minus 27.2. That's twice 13.6. And here you get at the state number 2, right? You substitute n equal to 2. You're going to get minus 6.8. This is number 4. K2 squared. And the kinetic energy is positive. And when you combine positive kinetic energy and the potential energy, you're going to get something that is negative. Okay, kinetic energy is 13.4, and you substitute n equal to 2, that's number 4, you're going to get 3.4 electron volt. And when you combine that, you're going to get minus 13.6 divided by 2 squared. So it's going to be minus 3.4. And in the second question, find the wavelength of the photon emitted from the electron transition to the state n equal to 1. From n equal to 1, we assume that the initial state is n equal to n, the final state is n equal to 1. You will need to get back to n equal to 1. So when they say the wavelength, right, you see that the wavelength appears here at the left hand side of the Lindbergh formula. And NF final is number 1, NI is number 2. So you're gonna get for minus 1, which is 3.4, right? This is 4 by 4, and 1 by 4, 3 by 4 is 4 by 3. 4 by 3 divided by Lindbergh constant. Okay. You can get the wavelength. Okay. Yeah, HC. HC. There are many ways. If you calculate it straightforward, you can get something. Finally, you get the wavelength of 121.553136 nanometer. Not only that possible release energy, but also many series that can occur. Okay, there are also many series that can occur. For example, any electron in any orbit. Okay, when that electron fall down to the energy level number 1 when n equals to 1, okay, you're gonna get also the photon. And energy is greater when your electron jump more and more. Okay, when it changes its place more and more, you'll get more energy because it releases more energy, okay, in terms of photon. 521, 421, 321, or 221. Okay, this is called Lyman series. Okay, Lyman. And for whatever this is invisible to human eyes, okay, the Lyman series, but the one that is important is Barnum series. Okay, Barnum series starts from any electron orbit, and it falls down to the orbit number 2, okay, the second orbit. And accidentally, this lesion could be seen by human eyes. So it is observable by human eye. So this might be interesting for us because whatever illumination, okay, if the human can benefit from that way, will can be made to make money. Okay, and we can sell it as a product or as the patent. Okay, but if you go further higher, okay, for whatever orbit level, and if the electron falls down to orbit number 3, or quantum number, the third quantum number, the quantum number is equal to 3, you're gonna get Hartman field. Okay. But this region is not observable by human eye, so it's not meaningful, right? Here you have Lyman series. This is written in the straight line diagram. Barber series inverse, Hartman series, bracket series to n equal to 4, and full series, K to number 5. 1, 2, 3, 4, 5. Okay. And so physicists discover this series by using special device. Okay, apart from the series by Barber, which can be observed by human eye. Okay, when you cannot see that when the electron share the principal level in quantum. is getting larger and larger, greater and greater. You can see the distance is not so much. Okay. Distance is very close to each other. Here is the energy level diagram for the hydrogen that shows some transition corresponding to various series. Okay, this is shown in the circular diagram. The ultraviolet can be the photon that is emitted from any quantum number, any electron orbit to first quantum state, n-1. And the visible light, that's boundary. Okay, boundary is the light. So yeah, that's visible to us from whatever electron shell to electron orbit number 2, n equal to 2. And the partial series, if you go further to the third electron orbit, to the fourth is going to be bracket series. Those are the series that produce infrared, okay, that is not easily observed by, that cannot be easily observed by human eyes. And n equal to 5, that's called full series. Okay, that's even harder for human eyes to reach. Okay. Realize that we would pay attention to the binary series because it's observable to human eyes. The binary series of the hydrogen atom, of course, because we start with the simplest case of the element, that's hydrogen, which has only single electron or single proton, and it corresponds to the state with Barber would have the electron reaching n equal to 2. Okay, this electron orbit. This is shown in figure 21 until figure 23. Let's talk about the example in the Barber series, which is the region where human eye can detect by the loveless wavelength of the emitted photon and its frequency, and then find the shortest wavelength of the emitted photon. First of all, you need to know that for whatever kind of wave, the longer the wavelength, the less the energy, right? You can get from that electron again. So when they ask you to determine the longest wavelength, that would correspond to, or that would imply the electron orbit that has the least energy, right? And regarding the shortest wavelength, it means it would correspond to the photon that has the highest energy. Okay, the minimal amount of the energy would be from shell from level n equal to 3 to level n equal to 2. Okay, because that's the smallest amount of energy that we can get, and this will correspond to the longest wavelength. And the shortest wavelength would mean the highest, the light that has the highest amount of energy. So it means you should start from n equal to infinity, and the electron should fall down or reach the orbit n equal to 2. Okay. This is our power field. short wavelength and long wavelength. You take max right because you want to longest. And from the feedback formula you get some release. And NI initial stage is going to be good. Okay, because longest wavelength implies least energy from the phone. 3 to 2. Lambda max is number 3, and once you substitute, you're gonna get the wavelength of 656 kHz frequency per emitter photon. It's just C by that wavelength. You're gonna get the frequency in on the order of 14, which is quite high. Okay, the energy of the photon in the minimum case will be a constant, and the minimum value of the get 1.8. The short wavelength will correspond to the highest energy level. You start from n equal to infinity, and your electron would reach the second orbit, n equal to 2, and now you substitute it into the feedback formula. You can see that NI minimum will be the shell that can produce the maximum amount of the energy is at infinity. And lambda, the minimum wavelength, can be derived from the wavelength from the energy state. Okay, when you substitute NI going to infinity, you can get number 1 right here. And it's going to be 4 by minus, and that corresponds to 364 nanometers. Please take the answer again. This is reasonable and 656. And here is 364. From electron energy at the in quantum state, both will provide atomic radius, okay, which is given by Soro resolver. Rn is h squared, h squared by mass of electron, k of electron, ke, and electron charge, what is k? What is KE in this scenario? K is the Coulomb constant. Right here. Okay, K is the Coulomb constant. Why is that? We're gonna get 0.05293 Sem. The other unit of this calculation is in nanometer. The atomic mass unit U is defined as 1/12 of the mass of the carbon-12 atom. It's quite useful, especially in the next chapter, atomic mass unit. It just, of course, there are many isotopes, many versions of carbon, right? One of the most stable is carbon-12 that can fall easily on Earth. Now let's compare three major components in the electron, but it's not the smallest particle. We have characteristics of neutron, proton, and electron. You have a symbol. Okay. Neutron is written as n with the power of 0. On the left hand side we have 1 and 0. N is the number of protons. Number 1 here is the on the left hand side is the number of nucleon. 0 means the number of proton because neutron is not proton, so we have 0 right here. Or you may write P with the power of plus, or you may write P11. P11 means here. The above number here represents the number of nucleon. Nucleon is the particle that can be either neutron or proton. We have 113 means the number of nucleons is 1. And the number of protons, because this is protons, these numbers could be counted. So it's number 1. And electron is written by E with the power of minus. Okay, because if you want to mention the charge value, you may write E with the power of minus some. Or in terms of atomic number, it's going to be E and 0 minus. We say 0 because there is no nucleon to this one, but we have -1, which is the number of protons. Because this is the opposite charge to proton, it's the electron, right? So it's going to be -1 for electron because we don't have atomic number. The ratio of now we will talk about the location we can find each particle inside the atom. Of course, neutrons could be found in nucleus. Okay, mu and nu can have some relation to each other. Protons stay at the nucleus, so we could find only the nucleus. Electron is a tiny particle that can move around the nucleus. Okay, that's called electron orbit. Their location. In terms of tiny mass, 10 to the negative 27, neutron is 1.67, proton is 1.67. The mass for both particles are quite close to each other. Okay, but the mass of electron is very, very small. It's even less than 10 to the 27 and 10 to the 31. Okay, these are all in on the order of 10 to the 27. And the mass of the particle divided by the mass of electron, okay, this turns to be a ratio. This ratio could be found as 1042 And the ratio, this ratio for proton is going to be 1.00. And the ratio between proton and electron very close to each other. That's mass the electron divided by mass of it. When you have at the third column the information of electron, it means you divide mass of particle by mass of electron and mass, so it's number 1. The mass in terms of atomic unit, which is 1/12 of the carbon 12. Neutron is around 1 atomic unit, 1.00. The same holds for proton, but proton has a little bit less amount of mass, okay, in terms of atomic mass. Electron is even smaller, okay, at the fifth point, I think, yeah, fifth point after the decimal point, 50. Mass of each particle can be expressed also as electron volt per c square, okay, because in nuclear physics you're going to need to change convert tiny amount of mass to be energy, so it's E equal to mc square, right? So if you want to find a mass in terms of that formula, you're going to need to divide the mass electron volt by the speed of the light. Neutron, when you compare it to the speed of light, is 939. Proton has also a similar value, 938. So the mass of proton and electron is even less than that. Okay, it's only 0.11, 0.511 in mega electron volt per c square. Let's talk about the chart. Neutron can be found from the typical formula for the quantum calculation. So for the particle physics, because it has one. Where is that? I forget the number. Here it has 2 up quarks and 1 down quark. Up quark corresponds to 2/3. Down quark corresponds to minus 1/3 of the whole charge. Wait, no, not this one. Okay, right here. Because neutron has only one up quark and 2 down quark. So when you combine it, it's going to be to remain 0. Okay, 2 of these things, which is negative, we have 0. So the neutron doesn't have any charge at all according to this particle physics. Let's talk about proton. Proton has 2 up quark and 1 down quark. 1 up quark corresponds to 2/3 and 1 down quark corresponds to minus 1/3. When you combine each other, you're going to get 3/3, which is only number 1. And let's talk about the charge of electron in comparing to the electron. It's going to be minus 1. I'm not sure whether it's negative or positive. I think it should be. Okay, spin number, spin behavior is one half for these 3 fundamental hydrogen. Okay, the number of protons in an atom is unique to each element. Like you have lithium. Okay. Lithium is important for a battery company, right? But now they are going to shift themselves to the element in the same column, the same group, which stays lower than, a little bit lower than lithium. And it's Na, okay, Na means sodium, right? The number of protons in the nucleus of the atom is equal to atomic number. Okay, this is the beginning of the next chapter, which is denoted by that. In the neutron atom, the number of electrons is equal to the number of protons. The mass number of atom, which is denoted by M, is equal to the summation of the number of protons and neutrons in the nucleus. Okay, this is the principle to nuclear physics. Okay, something that resides in nucleus. A hydrogen-like atom is an ionized atom that occupies only one electron. So if you have helium that has two electrons, you have to throw away one electron. You're going to have only one single electron, as same as hydrogen. When an atom has an atomic number set, the term E squared can be replaced by needs to be replaced by Z E squared. You just multiply E squared, the charge square of the electron by the atomic number of that element. So according to equation 27, the energy level, because we have E squared right here, right? So we're gonna get E to 4, E with the power 4. So you're gonna get Z squared. And the number before that will remain the same, and that's the 30.6. The denominator will be the same. Okay, it's going to be the same. Lineback formula can have some effect from that. If you consider a bigger atom, okay, like lithium, Lineback constant has the electron charge is with the power 4 here, and that's why you get Z squared. Okay, you get Z squared comparing to equation 31, and that's the typical Lineback formula. And the radius of the Bohr atomic model is going to be the same number of 0.05293. But here we have E squared, the charge squared at the denominator. And here you're going to get additionally the atomic number of 7, right? It's going to be N squared. Please note that the radius will be greater and greater when you consider the higher orbit within large. And this is done with the power 2. Okay, this effect will take place with the power 2 N squared. If you consider bigger electron orbit, the radius will be also bigger and bigger with our power 2. All right. Now let's consider the first element that can apply the idea of the hydrogen atom. The next element to hydrogen is helium. Helium can have several isotopes, helium-32, helium-42. Whether you have one neutron or two neutrons at the nucleus of helium. Okay. Atomic number is 2 because the number of protons inside the nucleus of ลูกเพื่อนของใครเนี่ยตกพื้นแล้วเดินเหยียบกันลูกใครลูกพัดเหรอตกพื้นเลยอ่ะมียืนยันด้วยเดี๋ยวเหยียบกันโอเค The number of protons residing in the nucleus is 2. And atomic weight, this is quite different from the number of nucleons. Of course, you would have helium-42, right? Helium-42, you would have 2 neutrons and 2 protons, 2 neutrons and 2 protons. The number of nucleons is integer, is 4, because you have 2 neutrons and 2 protons. But the mass is different. The weight, actually it's not weight, it's called weight because we need to differentiate this value from the mass. And that's the atomic mass number. Okay, the number of nucleons sometimes is called atomic mass number. Here is atomic weight. Atomic weight means there are some effects inside the nucleus. Proton has some effects to neutron has some effects to neutron, so on. So it's not going to be 4 exactly, it's 4.002602. The unit of this one is atomic mass unit, that's U, okay, 1/12.
Oh my god.
Of the carbon 12. Okay. Yeah, we use HD to represent this atom, so it's helium, right? And electron configuration is 1:2 because that's the quantum number, principal quantum number of 1. S is the first shell, right? First shell. You're going to see it later. And number 2 because we have 2 electrons in the stable version of helium. Okay. And the structure is crystal. Okay. And they use dot. You're gonna get helium at 20 degrees of Celsius. Like it's gas. Okay. This symbol means gas. Okay. Dot means air. The atoms of helium are quite far from each other. Okay. That's gas. Encyclopedia Britannica from Britain. Helium has the relative atomic mass or atomic weight ArH2. Okay, is denoted by here. Atomic mass or weight. 4.00262 this level and the atomic number is set equal to 2. Of course, when they talk about singly ionized helium, it means usually helium has 2 electrons, right? And you throw away 1 electron out of the okay, you're gonna get you're gonna miss 1 electron, but that electron should reside in the orbit as same as the one. And in a similar way to hydrogen. As an electron in an orbit denoted by n equal 1. When the atom is in its ground state, the lowest energy is ground state. Find the energy in the ground state in electron volt. You need to use that formula here. Okay. Because that is equal to, so this number will be number 2. 2 squared will be 4. And when you want to observe the energy at the first layer of the ground state, n equal to 1, substitute those z equal to 2 and n equal to 1 in this expression. You we're gonna get the energy level in electron volt. Get the unit of electron volt. Okay, 2 and 1. Number 2 and number 1, you get something like this, and that's in electron volt. All right. The next one is the radius. They want to know the second quantity, which is the radius of the ground state orbit. It's 0.0395, 293, 0.05293. And you're gonna need to have also the expression for the atomic number, okay, and the denominator, and here is the electron orbit, n equal to 1. You substitute n equal to 1 and set e equal to 2 to equation 53, you're gonna get the rate in nanometer. Okay. Please note that this corresponds to 10 to negative 10. Okay, and usually we're going to say that the size of atom is on the order of 10 to negative 10. And that's simply called Angstrom. Angstrom is the same name, same word from the electric company in France, Angstrom. Yeah, we get 0.02645, which is a bit smaller than the pure 9%. Okay. Because this thing is very complicated. Human try to capture its behavior. Now let's consider the doubly ionized lithium. Lithium has 3 protons, right, and 3 electrons in the typical state, in the equilibrium state. When you throw away 1 electron, you can have 2 plus charge, right? So this is the excited state. The first stage, assume that the electron is not in the ground state, n equal to 1, but rather in the first excited state, n equal to 2. Lithium has the number of protons as 3, right? So we have 3 protons inside the nucleus of lithium. And because you would have you have 4 neutrons and you have 3 protons, it's going to be approximately the same. But atomic weight is around 6.938 and 6.997. All right. The symbol is Li, it's lithium, and electron configuration is 2s1. You have the electron in the second quadrant, is the third. The third electron is inside here. And acid base property. Okay, you know lithium is made for modern electrical vehicle battery. And it's made of higher valence oxides. It has crystal structure. You get crystal structure. This is also a crystal structure. Symbol is quite different. Body center is cube. Okay, crystal structure. When you have that, it means it appears as so. Okay, you can see it's not written in the pure white color, but rather in a with yellow. Yellow means alkaline minerals. It's a kind of mineral, but it's alkaline. It's really sensitive to other activities. This one is strongly basic. It's very acid. So when that element is acid, it's not good for you to touch. So lithium battery is not good for human to touch because it's acid. The way is not precise, it lies simply in this region because of the finite precision in the measurement. Okay, atomic number of lithium that equals 3. Of course, they would like to know the energy in the first excited state. First excited state means you don't have n equal 1, but rather n equal 2. Okay, the state that after the ground state. Ground state means n equal 1, but this is the first excited. That's the level, next level higher than in electron volts and the radius, right? So you use same thing minus 30.4.6. And here is the Z square, right? The number of protons in lithium. So you have 3. And when you consider the first excited state, n equal 2, you're gonna get the energy. So energy would be a little bit larger due to the third element in the periodic table, and the energy will be smaller due to what you consider, which is called the second electron orbit or the first excited state. So you get minus 30.6 electron volt. Regarding the radius, it's going to be 0.05, 293, and here is the n square, right? The n square, quantum number state. And you're going to get, of course, here that equals 3 for the link. And after you make the calculation, you get 0.07. Again, we have something on the order of 10 to the 10 that's against Armstrong. Okay. Both theory in turn was supplanted by quantum mechanics. So there is more significant sophisticated theory behind both atomic model. And that's called quantum mechanics. Okay. But the idea is quite good. Now let's move to quantum mechanics. Before that, we consider the standard model of elementary particles. You have been taught that any substance, any particle should contain the most basic particles, which are called proton, neutron, and electron. Right? But it's not the case. Okay? Of course, the electron is one of the most basic particles. We are talking about elementary particles, okay, which are even smaller than protons and neutrons. In this color, in this region, it's going to be called quarks. Okay, quarks. You have the mass in terms of mega electron volt per c mass. And charge is going to be 2/3, and spin number is 1. But that is everywhere for highly quarks and leptons. 3 generations of matter is going to be up quark, sharp quark, top quark. Okay, when you accelerate the particle, you're going to get can see bigger elementary particles like sharp quark, top. You can see that the mass is bigger and bigger, greater and greater. Okay, so to make up this 1.28 gig. The 173 gigavolt gigabits into 9, right? And here is downward. Okay, the negative version in sharp. Okay, this 2/3 and negative 1. Okay. Maybe 1/3 into 1/3. That's the sharp. The mass is quite close to each other, 2 by 2 mega electron volt per square, 4.7 mega electron volt per square. Hence, strength quark, which is even bigger than the dark quark, and quark. Each of these 6 particles would have the antiparticle. Antiparticle means you have a charge that is opposite to what we had before. Okay, like the anti-up, anti-charm, anti-top particle. Okay, and the mass will be the same. Okay, whether you have the forward particle or the anti-particle, like anti-up, anti-charm. The downward one would have also anti-down. The mass will be the same, 4.7, 2.7. The difference between downward and anti-downward is the charge, which is here minus 1/3, and then you have plus 1/3. And anti-strange, okay, is a big version of anti-down, okay, in the same way as strange quark and bottom quark. Okay, anti-bottom is even bigger than the anti-strange. Okay, this is called fermion. Okay, it has something to do with oligofamily. It's called fermion. And this one is called lepton. Okay, this one is called boson. There is an Indian physicist whose name is Boson. Okay, his name is Boson. And the boson would rely on the statistic, which is discovered, which was discovered by the Indian physicist. His name is Boson. Okay. And the fermion can be described by mathematics, which was derived by oligofamily. Lepton is a tiny particle. You can see that the mass is less than, much less than quark. But the bigger version of the lepton is also significant, not so small. Like you have electron, the bigger version of electron is called muon. You cannot find muon and tau lepton easily in daily life. You need to accelerate the particle for a long distance, and you're going to get the chance to see bigger leptons like this, like muon and tau. And those 2 electrons particles, those 2 electron particles will not be stable. Once you have electron, the antiparticle to the electron is called positive. Okay, the spin number is the same, mass is the same, but the charge is different. It's positive. Positive cannot be found easily. It's called beta plus particle. Electron is known as beta minus particle. And again, the antiparticle to muon is called anti. All of these can be noted easily when they have bar, except for proton. Proton just simply use the positive side on the right superscript. Wow. The mass of anti-neutron is the same as the mass of anti-tau is the same as the mass of tau. And you can see these electrons and sharp minus 1 or positive. There is another kind of electron that can be detected difficultly. Okay, it's hard to detect this kind of electron. It's called electron neutrino. Okay, the mass is even smaller than electron. Okay, but yeah. That was surprise discovered by modern physics. Up until now, humans cannot measure the exact value of the mass of electron neutrino. Neutrino would be written with nu. Okay, nu is an alphabet of Greek, right? Electron neutrino, and the neutrino cannot be detected easily. So because the charge of the neutrino is zero, it doesn't have any effect to electric field or magnetic field. So it's very difficult to measure the behavior that we have. So we have muon neutrino corresponding to muon. We have tau neutrino, which is a bigger version, H equal to. And we have electron antineutrino, okay, corresponding to the first one. We have muon antineutrino corresponding to antineutrino. We have tau antineutrino corresponding to tau. These are called boson. These are called boson. Oh, sorry, these are called fermion. On the right side is called boson. It doesn't have meat. Usually it doesn't have so much mass. Okay, like gluon. Gluon has only spin number, which is number 1. And the next one is photon, which is what we just studied. It has spin number 1. There is no charge, there is no mass, and Z zero. The Z boson is the hard boson that has mass. The spin number is number 1. Okay, and W plus boson, and W minus boson. Okay, W plus and minus has the same value for mass, but the sharp value is different. Okay, boson has W minus boson has -1 sharp. Okay, this is gauge boson or vector boson, and here is scalar boson. Okay, the one that was recently discovered is Higgs boson. Okay, you know Higgs is the surname of a professor. I think he is from Scotland. He is still alive, but he is very old. He is 90 years. Blah, blah, blah. Okay, that's dedicated to him. Okay, Higgs boson. I think he worked sometime with Sem, the research institute to that study something about tiny particle. Let's talk about our basic element, atomic component, and that's proton. Proton has 2 quarks that you have seen earlier. We use different colors to represent a quark for some purpose, which is very deep, apart from what we need to know in the primary, in the secondary school. And we have one dark part, which is denoted by the green. And out of these 3 protons are connected or joined by the gluon. Gluon is this one. It tries to combine all these 3 particles to become a proton. Okay, like this. You can see the one quark corresponds to the 2/3 charge. 2/3 minus 1/3. So 4 minus 1 is this way. So that's why the proton would have 1 positive charge. Okay. Next one is neutron. Okay, neutron have something different. They have both up and down, but the number of dark quark right here is greater than the number of quarks. So you have dark quark one single apart. This is 2/3, this is minus 1/3, minus 1/3. So the charge will cancel each other. So that's why neutron doesn't have any charge also. Neutron has zero charge, simply speaking. But these three bosons are joined by nucleon. They are three groups. Okay. And there are many effects after that when you try to destroy one neutron or one proton. Now we arrive at the wave particle duality. In 1924, a French physicist, his name is Louis de Broglie. Okay, he suggested an idea when the electron is not actual particle, but it's rather a wave. Okay, it's called wave quality. The electron can also behave as wave. When we have mass of electron as they moving with speed of v and the wavelength number. Of course, regarding the classical physics, we have momentum p which is equal to mv, and the wavelength in his idea can be found from h by p, okay, which is the maximum constant, and p is the momentum of the tiny particle. You can also apply this idea to bigger particle, like tennis ball. Okay. He divided by mv. All right. He asserted that this relation holds for, and he believed that his idea holds true for electrons, for protons, and all particles. Let's consider this example when the mass of the neutron is soon to be 1.675 10 to the 27 kilogram. It's very small amount actually. And the speed is the quantity that needs to know, and also kind of energy the neutron. When they have the broad wavelength of 0.2 nanometer, so if you want to find the speed, you need to use lambda is h by mv, right? So you move v to the left hand side. I think the time is over. We're going to quit this lecture. So see you next week. Okay, ครับ สวัสดีครับ บ๊ายบาย 14-20 ใช่ป่ะหมดเวลาละเดี๋ยวอาจารย์อีกช่องหนึ่งเขาจะมาว่ารู้สึกจะเป็นไบอันมั้งต่อผมเนี่ยใช่ไหมใช่ครับคุณก็เรียนภาษาอังกฤษไปกับไบอันแล้วผมไม่เปิดปีภาษาไอ้แอนจอยไม่ใช่แอนไม่ใช่จริงครับไอ้เหี้ยสติไปในที่นี่ว่ะปักยกกล้องไปที่ห้องนู้นหน่อยครับยกกล้องเดี๋ยวอาจารย์เนี่ยไปสาวไปหาลูกออกที่มีโทรศัพท์ครับรอยกันไม่ทันนะยกกล้องให้หน่อยแบบไหนสัตว์อันนี้คือมันเปิดอะไรมันเปิดสะอาดเขาแค่ต้องครอบกันไม่อยากอะไรเลยวงมองต้องอยู่ด้วยกันสมาธิสั้นฟาดเดี๋ยวคุณพาเขาไปดูก่อนเปิด6 อันพร้อมกันนะครับ6 อันพร้อมกัน6 อันแล้วเอาอีกไปห้องนู้นเดี๋ยวครับสวัสดีครับอาจารย์สวัสดีครับอากาศดีนะครับวันนี้อากาศดีครับเขาทำให้คุณเย็นขึ้นด้วยการฉีดน้ำด้วยครับโอ้จริงป่ะครับนี่ครับเขาฉีดน้ำอันนี้จะรอทิชเชอร์ไบอันนะครับทิชเชอร์ไบอันยังไม่ออกมาเลยครับ แดนฟ้าบ้านอยู่ไกลไหมครับจากโรงเรียน
ปากสองครับเดี๋ยวมอบางแค
โอ้
ก็ไม่ไกลครับ
เนาะก็อยู่ฝั่งนี้เหมือนกันเนาะไอ้เขาข้ามไปอีกฝั่งหนึ่ง
อันนี้ฝากข้าวอีกฝั่ง
แต่มันก็ไม่ไกลอันนี้มันชิดแม่น้ำแล้ว
แต่ผมว่าไม่ไกลเท่าจานแหละ
ครับผม
จานนี่
ข้าม2-3 จังหวัดครับ
จานอยู่จังหวัดอะไรนะครับ
ผมอยู่นครนายกครับตอน
น
นี้
ครนายกแต่จานเป็นคนจานเคยอยู่กรุงเทพครับ
ผมอยู่กรุงเทพ10 ปีครับ
โอ้
ผมเรียนมปลายที่เนี่ย
อ๋อ
ในกรุงเทพแล้วก็
แล้วทำไมกลับไปนครนายกครับ
เพิ่งไปสมัครงานที่นั่นได้
แล้วก็อยู่มาตลอด
ก็อยู่ไปเรื่อย
เมืองเขาใหญ่เท่ากรุงเทพครับ
ๆโอ้เล็กมากครับ
อำเภอเมืองนะครับ
ใช่โอ้ยเท่ายังไม่เท่ากับเขตหนึ่งของกรุงเทพแล้ว
จริงไหมจ๊ะ
ตัวเมืองเขา
กรุงเทพทีไรจานก็แบบแปลกๆแค่
โอ้อึดอัดเลยครับใหญ่เมืองใหญ่รถติดแน่นหนาเลยที่เนี่ยครับ
มันใหญ่มากเลยนะจาน
ใช่แต่ผมก็อยู่มาแล้วแหละ ผมก็เคยอยู่มาแล้วกรุง
แต่
เทพ
เมื่อก่อนรถไม่เยอะเท่านี้แล้ว
ใช่ใช่มันก็เยอะเหมือนกันแหละครับ แต่อันนี้ยิ่งเยอะเข้าไปเรื่อยๆแล้ว10-20 ปีผ่านไปกรุงเทพก็เปลี่ยนไปครับถนนหนทางก็แตกต่างจากเดิมโอ้โหสวนกุหลาบนี่มี 11 สาขาเลยอะเยอะมาก
มีกลับแล้วมีสระบุรีสงขลาด้วย
สงขลาก็มี
มีลงใต้ด้วยอาจารย์ครับกันนะ
เขาต้องมานี่ด้วยนะเวลาประชุมเนี่ยนะโอ้ไม้ก็ผมเห็นมีรังสิตมีปทุมธานีเมื่อกี้นะ
รังสิตยังไม่เท่าไหร่แต่ปทุมก็ไกลแล้ว
ปทุม
มี
เนี่ย
สวยมาจากชลบุรีถนนนนทบุรี
รังสิตนี่ผมก็ถือว่า ใกล้กว่าผมนะผมเนี่ยไกลกว่ารังสิตสวัสดีครับสวัสดีครับ
ฮะไอ้คูดี้อยู่ไหนเอาทำไมอ่ะไปไม่มาเอาเหรอเป็นสัมภาษณ์วันนี้เหรอเฮ้ยมีที่เรียนแล้วเว้ย
อาจารย์ครับ
มาเลยมันฮะ
ได้ครับได้
ภาษาอังกฤษ
เดี๋ยวรอบหน้า
เพิ่งเสร็จเพิ่งเสร็จเนี่ยฮะอันนี้เมื่อกี้เพิ่งเรียนฟิสิกส์เฮ้ยฝากวันนี้คูดี้ด้วยเจอกันเพื่อน
No problem, no problem. Take your time.
เชื่อไวเลยล่ะจะครับวางไว้ไหนดีครับ ได้ครับ
อาจารย์ครับเดี๋ยววันนี้จะมีคนมาคุณจะไปเรียนเสร็จแล้วเดี๋ยวกลับมานะ
หมายถึงคุณไปวิชาอื่นนี้เหรอ
นะครับแค่แป๊บเดียวครับ
ho 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 ho
ไม่แค่วิชาอื่นแล้ว
สายป่านต้องไปวันนี้เหรอสวัสดีครับก็มันอัดอยู่ใช่ไหมอ่ะ
วันนี้เรียนอะไรครับ
วันนี้เรียนอะตอมิกฟิสิกส์นะครับเป็นฟิสิกส์แผนใหม่เนาะเราไหวปัญหาเดิมนี่หว่าโอ้
ไม่เป็นไรไม่เป็นไร
มีไม่กี่คนได้ป่ะ
ครับไอ้แดงๆขึ้นอย่างนี้นี่มันมีปัญหาไหมหรือว่า
ไม่น่าโดนอัดนะ
ไม่มีอะไรใช่ไหมอาจารย์เพราะมันอัดอยู่แต่ว่าอัด
เล่นมันยังวิ่งไม่เป็นไรครับ
โอเค
มีมันจะเต็มหรือเปล่าไม่รู้เดี๋ยวเรา
อาจารย์บอกว่า2 ชั่วโมงที่เต็มเลยนะเกือบเต็ม
หนึ่งเวลาแล้วนะโอ้โหเพราะว่าจะมีคลิปเก่าอะไรอย่างนี้ด้วยให้ลบด้วย
เอาดีกว่าลงเรียบร้อยครับแค่ไอ้คลิปนะที่เป็นจูบมึงอยากไปข้างนอก
เต็มแล้วหรือยังเลยแอปไม่งั้นก็หยุดลบคลิปเก่าก่อนดีกว่า
อาจจะเต็มกลางคันใช่ครับมันน่าจะไม่บอกว่าใกล้เต็มเลยสักอย่างไม่รู้เพราะ
อะไรอ่ะวิ่งอยู่หรือเปล่าเนี่ยน่าจะวิ่งอยู่
ทัดของคน
เซตอะไรสักอย่างโอ้ยังมีทั้งการ์ดทำกันเต็มที่เลยนะครับโน้ยเราเทลิโฟนจะเช็คแนวชานนท์เหมือนเห็นอยู่ตอนหรือเปล่าเลยวันนี้604เอาคราวที่แล้วไม่มีใครพลาดเลยนะที่นี้ครับป่านนี้ที่ครับกิจภูทิพย์ครับกิจภูทิพย์ไอ้อยู่แถวนี้ไม่ใช่เหรอกิจภูทิพย์นะไปว่ากันฮาราอยู่นี่นะแล้วก็การกรนะครับการกรหมายเลข 3ใช่หรอธีรวิทย์สุขีเราพิพลนี่นะใส่เสื้อกันหนาวนี่คือตอนเช้ามันหนาวเลยหรอกลางวันนี่ไม่ได้หรอกพิมพ์ศิลป์ครับพิมพ์ศิลป์นี่คนตัวคะแนนท็อปของโรงเรียนเลยใช่ป่ะไม่ใช่หรอผมจำชื่อใครสับสนแน่นอนพวกห้องอินเตอร์นี่ดีนี่แบบกองอยู่ต้นๆของโรงเรียนก็มีเหมือนกันภูมิเต็มภูมิฮัลโหลคุณมีสมาธิในการเล่นการ์ดของคุณมากนะเรียกไปทีทัศน์ครับทีทัศน์ครับพิชานันอยู่ด้วยกันครับผมแล้วก็พัดขาชินครับศิลวิทย์นั่งนี่โปรแกรมเมอร์ไปไหนแล้วลาโปรแกรมเมอร์เป็นไรเนี่ยไม่สบายหรืออะไรทีนั่งนี่ไปห้องน้ำเห็นแล้วผมว่าทีนี่น่าจะเป็นคนเดียวที่ผมคิดดีเขียนเลคเตอร์จากใจเพราะว่าเขาเป็นพื้นตัวดีธนาวิทย์นะครับธนาวิทย์ฮัลโหลธนาวิทย์ใช่ธนาวิทย์ไม่เจอสตูดีรัตนะครับโอ้ใส่เสื้อกันหนาวหมดเลยนะครับเดี๋ยวนี้ชีวกรจะไปห้องอัตพลแอลทางนู้นนะครับนี่แทบจะไม่เปลี่ยนที่นั่งเลยกลุ่มโซนเนี้ยไม่ค่อยเปลี่ยนที่นั่งนอกนั้นเนี่ยนับชยุทธพลหลับจริงหรือเปล่าเนี่ยดูหน้าหน่อย เป็นคนห้องอื่นหรือเปล่ามานอนอยู่นี่อ๋อใช่ปล่อยของมันไปก็ก่อนครับก่อนอยู่นี่ก่อนไปไหนก่อนอยู่นี่ครับฮะสนามวิทย์นะที่เรียกไปก่อนนะกินบูทิพย์
โทษทีครับเมื่อกี้ชายงานอยู่
ศิวกรมายังอภิโชตครับผม
อภิโชต
แล้วก็ชานนท์ครับผมโรงเรียนสาธิตผมสอนเมื่อวานนี้สอบกลางภาคตกเหมือนพวกคุณทานอยู่ไม่กี่คนแล้วมีให้ซ่อมด้วยครับซ่อมฮะสอบกลางภาคเขาสอบไปแล้วกลางภาคยังไม่ได้ไปมีตกด้วยนะเขียนโปรแกรมแล้วประมาณนั้นกมลสิทธิ์ของกมลสิทธิ์เรียบร้อยวันนี้สุภรัตน์ตอนแก้วสุภรัตน์นัทพลเอ็นทางนี้นะครับพานั่งด้วยกันครับนัทธนนท์อาริยวุฒิอยู่นี่นะภูริศักดิ์นั่งนะครับแล้วก็วสันตพัฒน์เมื่อสุดท้ายอยู่นี่มีใครหายไม่มีนะมีศิลวิทย์นะยื่นจดหมายลาด้วยนะห้องนู้นนั่นขาดเต็มเลยนะ1 คนไม่ได้ส่งข้อมูลว่าจะอยู่หรือไม่อยู่อะไรเลยเขียนขาดเลยนะแอปเซนต์เลย1 คนขัดขนมแต่ห้องนี้ผมไม่น่าต้องกล่าวอะไรนะห้องนี้ไม่ค่อยน่ามีปัญหาเพราะว่าสิ้นเดือนนี้นะครับเขาให้ผมส่งสถิติการเข้าเรียนของคุณครับคนไหน ไม่ถึง80ชานนท์เนี่ยน่าจะมีปัญหาคุณก็ไปคุยกับเจ้าของอีพัทซึ่งคือใครเขาเรียกอะไรดร.โชคครับไม่ใช่เจ้าของเขาเรียกว่าหัวหน้าอะไรคุณก็คุยกับหัวหน้าอีพัทนะครับว่าเกิดอะไรขึ้นกับคุณแค่รายงานตามความเป็นจริงให้เขานะตามไปโอเคห้องนี้ไม่มีนะ letter recommendation มีธนากรห้องนู้นนะนั่นจะไปเรียนอเมริกาอะไรสักอย่างเลยOkay, good afternoon everyone. Welcome you to เก้าอี้นี้มันขยับตัวลำบากเปลี่ยนอันดีกว่าจริงมันนั่งสบายนุ่มนิ่มนะแต่ว่าไม่สะดวกเดี๋ยวไปโดน iPad ทุกอย่างนี่อันนี้มันลุกง่ายกว่า Okay, let's continue our content in electron orbit, especially some characteristic of electron orbit behavior, whether it's going to be electron orbit energy, or the radius of each orbit. Okay, that's great. Okay, because some of our grandfathers, okay, the people in the previous generations have already discovered something useful to us. So we get to know some deep detail of the tiny particles like the electron. Okay, so as you know before in the last lecture, จบแล้วเนี่ยมันแวบๆนี่คือมันตัดอยู่หรือเปล่าให้หรือว่ามีปัญหาเมมโมรี่
หยุดแล้วเนี่ยตัวเลขวิ่งอยู่วะอันนี้เมมน่าจะเต็มแบบหน้าเมมน่าจะใกล้เต็มผมไม่ได้ลบของ3 ชั่วโมงกับคุณคราวที่แล้วครับ
มันยังอยู่ในเครื่องแล้วมันกัด เอาไม่งั้นผมต้องซื้อ external hard disk มาจ่อไว้เลยดีกว่าเพื่อความชัวร์โอเคhave seen there are two kinds of energy พวกผมเสียวอันนี้คุณเหยียบลูกปิงปองเลยเดี๋ยวมันจะเสียหายมันจะแตกกว่าไว้ข้างบนดีกว่าวางนี้ก็ได้ถ้ามันตกจากโต๊ะคุณมันยังตีได้อยู่นะครับไม่นะเสียดาย Okay, as you know, there are two types of energy. The first one is potential energy, right, which is derived from Coulomb force and so on, and you end up with energy. And another one is the kinetic energy, okay, which is derived from 1/2 mv², right? And it turns out that the kinetic energy is positive, but it's 1/8. And the electrostatic potential energy, which is derived from the Coulomb force, is negative, and it has double in magnitude of the kinetic energy. So when something that is greater than another value, which is positive, the summation of all terms would turn to be negative value, okay, which is 1/8 of that star. And once you substitute everything, then you is not your effort. Someone has already tried to investigate that for you. The physics in our previous generation. When you substitute the mass of electron and the Coulomb constant Ke and the charge of the electron K with the power of 4 here, and here is the reduced Planck constant, which is h/2 pi, and n², which is the quantum numbers. Okay, the principal quantum number or the quantum state number. You're gonna get simple number, okay, with after approximation. Actually, there are some more digits after the decimal point, but for us in the high school level or secondary school level, we are going to take only the simple number like single digit after the decimal point. That's 13.6. But as you know, this is the negative value, so we still have the negative value here. Okay. นะเขาก็ละเอียดมากเลยนะพวกรุ่นคุณปู่ถ้าคุณปู่ผมด้วยนะนะครับ2 เจเนอเรชันที่แล้วพ่อของพ่อผมก็รุ่นคุณปู่นะลงทุกรายละเอียดทุกเม็ดเลยนะทุกตัวแปรใส่เข้าไปนะครับค่าคงที่ออกมาเป็น13-16เม็ดเลย Okay. The reason why we need to leave n² because we are to the shell or the orbit level of the electron. So we still have n, which is variable. N is an integer, okay? It's not continuous variable, it's not 2.7, 3.2, no. 1, 2, 3, 4, 5. Okay, only positive integers. Until infinity, so the energy here, which is denoted by capital E, should have the subscript of that number, okay, which is n, and we elaborate this energy to something that is more appropriate, and that in electron volt, EV. Okay, it's not electrical vehicle like in
our generator is electron volt. Okay.
Not EV electrical vehicle. Here is electron volt, and of course, n can start from 1, not 0. Okay, n small n here cannot be 0. If you substitute n equal to 0, it's going to be division by 0, and that's going to be infinity. It's impossible. Okay, n start from 1, and n can be only integer. N cannot be 0.5. Okay, it's impossible. The shell of the orbit of the electron can be only integer, not 0.1, 0.7. It's only 1, 2, 3, 4, 5.
You may suspect that what is the most far distant from the nucleus. So it's going to be infinity. Okay, the number is unbound, so you can get infinity for it. When you substitute n as infinity to this term, it's going to be infinity squared, and that's still infinity. Of course, it's going to be a number 13 or 6 divided by something very large, so this will tend to 0. So when you are very far from the nucleus of this atom, from this nucleus, you get 0 energy level. Okay. There will be no, of course, there will be no kinetic energy, there will be no electrostatic potential energy, because this one, this one depends on Rn. So if your Rn is very large, so you would have very little force on the charge. Of course, the electron can stay together inside the atom, because there is attractive force between positive charge and negative charge, right? And that turns to be electrostatic potential energy. When you are far from the nucleus, this energy will turn to be 0. You have 0 when your orbit is very large. And you may want to know the difference between the closest and the far distance. It's going to be E infinity minus E1. E infinity minus E1 means you have 0, right? 0 minus 13.6. Okay. 0 minus 13.6 divided by 1. Okay. E infinity minus E1. That's going to be 13.6. Okay. The unit is eV, electron volt. That's why we get this one 13.6 eV. And this is known with the special word as the ionization energy. The reason why we say ionization, ion means the atom that is not in equilibrium state, right? It's not symmetrical because one charge is dominant, right? So in this case, the electron is far away from the nucleus. It means electron doesn't have anything to do with the nucleus at all. It has no relation. So we can say that electron doesn't belong to that atom anymore. It means that nucleus has already lost the electron. So when the atom doesn't have its electron anymore, it means it's going to be ion, right? And this is called ionization energy. It means the energy that you will make an atom to be ion, okay? And that's called ionization energy. This is valid for hydrogen atom only. Now, if we look into the third assumption of Bohr, we're going to see that the wavelength of the electromagnetic radiation can be found from equation 15. Okay, equation 15. If you go back, it's going to be HF equal to E final, E initial minus E final, like this. Okay, E initial minus E final. When you want to study something about the wavelength, you have to convert F, which is the frequency, to wavelength by using the relation C equal to lambda f. But what we have is f on the left-hand side, so f will be C by lambda. You just substitute this expression to the left-hand side of 15, and then you get the new formula that has the relation. ครับโอ้ตามสบายครับตามสบายครับตามสบายyou're gonna get the relation to the wavelength. Okay, and because it's initial minus final, right? So initial would have its own negative value. Final would have its own negative value. Okay, and once you make the subtraction, minus and minus will be positive, will be plus. So NF will stand before NI. Okay. The final quantum number state and the initial quantum number state. They are NI should be greater than NF because you jump from a higher energy level to the lower energy level. Your electron jump in that case, right? Jumps in that way. It's going to emit the photon, the light or the energy, right? The energy in terms of photon. The frequency of that photon can be found from this relation. HF. F is the frequency. H is, as I always mention, it's maximum constant, right? And once you substitute the wavelength relation, C by lambda to this one. A guy from Sweden, okay, he is Swedish, his name is Lippert, or Rippler, you can say this Rippler. Just follow this way, okay? Lippert is the guy who was going straight forward. He just substitute the speed of the light vector, which is around 3 times 10 to 8 meters per second, and the Planck constant. Okay. Whatever the physics and that generation discovered, they are published widespread. Okay, widespread. So Lippert formed up a new formula. He moved H to the right hand side. He moved Z to the right hand side, and he just let them stay together, and it's going to be equal to a constant like this. Okay. This expression, which is actually the same thing as equation 30, but it's accepted later as the Lippert formula. Yeah, if you want to get also the Nobel Prize like Lippert, you have to follow this way. Okay, just simply substitute the value of the light speed and the Planck constant into a simple formula, and you get the Nobel Prize. And yeah, it turns out that after Lippert, ผมจะออกเสียงแนวเยอรมันเลยนะต้องอ่านภาษาอังกฤษจะเรียกว่าลิปเบิร์กใช่ป่ะผมออกเสียงว่าลิปเบิร์กนะคนที่อยู่ประมาณนี้ BERG จะออกว่าแบกนะครับอย่างเช่นสเตฟานเอฟเฟนแบกเนี่ยรู้จักป่ะก็เป็นนักฟุตบอลตัวหลักของทีมชาติเยอรมันไม่ได้ใช่ป่ะน่าจะง่ายไปอันเนี้ยผมว่ามันง่ายๆแต่ไม่ได้นะผมว่าดีไลท์สูตรแค่นี้มันไม่น่าแบบสมควรทำอะไรได้โอเคyeah, after he put several constants into this term, he got 1.09 into 7. Okay, of course, the quantum state number doesn't have any unit. In order to have the same unit as 1 by lambda, with that constant would be 1 by Okay, 1 by meter. That's the unit for feedback constant. Now we will see how useful the feedback formula is. Let's consider the second quantum state, n equal to 2. A second. Of the hydrogen atom. This is valid for hydrogen atom. Okay. The first thing that the first group that they would like to know is the kinetic energy, okay, and potential energy and the total energy. So it's the kinetic energy is the same as the total energy, but it's in positive way, right? Positive quantity. The potential energy is twice, but it's negative value. And total energy is minus 13.6 divided by n squared. Our n is 2, so 2 squared will be number 4, right? This is the potential energy twice 13.6, that's 27.2. You substitute n equal to 2, you get minus 6.8. Please observe that the potential energy is the negative value. And the kinetic energy, which is a positive quantity, is exactly the same as the total energy. In that way, the total energy is negative value. You have positive. You have 13.6 divided n squared. N equal to 2, so it's number 2. The number 4. 13.6 divided by 4 is only 3.4. And please note that the unit of energy in this topic is not anymore joule, okay, but rather electron volt EV. Okay, it's more suitable to this kind of energy level. And total energy, of course, En, when we consider n equal to is going to be the subscript of number 2, you will substitute n squared, right? N by 2, so it's going to be 2 squared. Divide 13 by 6 by 4, okay, so 13.6 by 4, you get 3.4. Sorry. Now it's time to apply the Rydberg formula. You can use his formula by using his specific constant, or you just simply use the typical formula from the NEMO model of the third assumption. By using that formula from NEMO, we get the final, right? Which is the initial state, right? Minus 3.4 and final is minus 30.6. H is the Planck constant in EV. ปิดได้หรือยังดับได้หรือยังครับยังไม่ดับใช่ไหมไม่งั้นผมต้องลบคลิปของผมก็ลืมลบคลิปของอะไรคราวแล้ว3 ชั่วโมงลืมเลยขึ้นเป็นได้แล้วก็เมื่อวานนี้ก็อัดของพวกโรงเรียนสาธิตด้วยนะสอบนะนำเสนอไปดูงานกันนะครับโลกเขาเรียกว่าสนามบินนะครับ That's the Planck constant but it's in EV version not Joule second version. Okay, it's in EV electron volt. You just divide by 1.602 times 10 to the 19. And the next one is the speed of the light, which is around 3 times 10 to the 8. เราอาจจะเช็คก็ได้นะว่าเล่นผมหรือเปล่านะขอบคุณมากครับคราวที่แล้วนะที่เช็คให้นะครับ Okay, very good. Thank you very much for checking. You will end up with 121 times 10 to the 9, or simply speaking, it's nanometer. Okay, you are dealing with the order of 10 to negative 10, that's uncontrolled, and the wavelength of the wavelength of the photon or the light that can be created from this scale is nanometer. So it's 100 nanometer. So it's around 1,000 times the size of atomic model. Well, Bohr is not a genius person. Actually, he has observed several experimental results from many scientists or many physicists. He observed the work from Lyman, from Balmer, from Paschen, and from Fund. Okay, but he is a great guy to propagate the idea that has some contradiction to the previous theory in physics. Lyman is the guy who observed the electron that falls down from any shell, from any orbit to the first state, the ground state, which is minus 13.606. Okay, that's what we have discovered before. Of course, when you are very far from the nucleus, you have zero energy level. Okay, there is no energy at all in that level when you are far from the nucleus.
ที่ energy เป็น negative เพราะว่าอิเล็กตรอน
อาจจะเป็นเพราะส่วนหนึ่งนะเวลาคุณแทนลงไปในค่า potential energy เนี่ยมันจะมีตรงเนี้ยถูกต้องนะเพราะว่า KQQ Q1 ก็คือชาร์จตัวที่ 1 Q2 ชาร์จตัวที่ 2 มันเป็นอินเตอร์แอคชั่นการทำกันระหว่างนิวเคลียสซึ่งมีโฟตอนเป็นบวกคุณจะแทน Q1 Q2 เป็นโฟตอนอะไรก็แล้วแต่แล้ว Q2 ก็คืออีกอันนึงก็คือชาร์จที่เป็นอิเล็กตรอนที่เป็นลบคุณเห็นว่าจังหวะเนี้ยมันไม่มีเครื่องหมายลบเห็นไหมมันเป็นบวกล้วนแต่พอคุณแทนชาร์จของอิเล็กตรอนเข้าไปซึ่งเป็นลบมันก็เผยค่าลบขึ้นมาได้เห็นไหมส่วน E มันคือ 1.6 อ่ะมันเป็นค่าใช้ได้ทั้งโฟตอนและอิเล็กตรอนตรงนี้ครับมันก็ถูกต้องคำของคุณก็ถูกต้องมันเกิดจากตรงเนี้ยที่เป็นลบขึ้นมาครับจะเห็นว่าตัว kinetic energy มันไม่ได้พลังงานจนมันไม่ได้เป็นลบนะมันเป็นบวกอ่ะแต่ว่ามันสู้กับพลังงาน potential ของประจุไม่ไหวเนื่องจากเขาบวกน้อยแต่เขาลบเยอะรวมกันแล้วมันก็สู้ลบไม่ได้สุดท้ายมันก็เลยติดลบอยู่ครับพวกคนนี้ละเอียดมากนะครับสอนรุ่นพี่คุณก็ยังไม่เจาะรายละเอียดมามากกว่านี้รุ่นพี่ไม่เห็นเจาะรายละเอียดเท่านี้เลยโอเคดีครับดีโอเค every energy level here that you have seen you can see that they are all negative values. So Lyman was the guy who observed the electron that falls down from any orbit to the ground state, the lowest level. You cannot say the zero level is the lowest one. It's not possible, okay? Because if you divide 13 by 0, it's going to be infinite. Okay. One is the first level that you can have. Okay, there is no negative integer. And this is called ground state. The second level, second orbit, is known as first excited state. I don't know, it's maybe similar to the floor, how you can say in how you count the number of floor. In American standard and in British standard, they use a different way to pronounce or to say the number of floor, right? Yeah, it's the same thing here. This is the first excited state. Okay, first excited state. It means it's not the ground state. It's okay. You put the energy to. You put the energy to electron, and the electron is not in the floor state. It's in the first higher level. It's called first excited state. Yeah. Lyman is the guy who observed when the electron falling down from the first excited state. of the second excited state to the third state. Okay. His result turns out that we cannot observe the photon easily by eyes. It's beyond the scope of human eyes. So it's denoted here by using the brown light. So it's not these photons cannot be observed by our eyes. But another physics, his name is Barber. Barber is another physicist who observed the electron that falls down from any orbit that's higher than number 2 to number 2, okay, minus 3.401. It's lucky that his result, with his result, the photon can be observed by eye, so it lies in the region of our human eyes. So, yeah, Bauer is quite practical because we can get the benefit from his results. Okay, if you want to produce the red, the orange, the blue, the green light, you can use his ring. Okay, from any orbit to the second orbit. Okay, that's great, Bauer. But beyond that, another physicist, whose name is Hunter. He also investigated the falling process of electrons from any orbit which are higher than number 3. That's called power pattern series. Okay. At that time, Nibo saw the study result from Max Planck and from Paschen, from Barber, from Lyman. Nibo is the guy who tried to combine this idea to the classical atomic model created by J.J. Thomson or Andy Rutherford and so on.
ก็คือมีหลายคนที่ดูจากเก็บสูตรมาคือคอมพิวเตอร์เบสิกเอเนอร์จีครับแล้ววอลก็คือครับใช่เขาก็เอาของทุกคนมารวมแล้วไปประสานกับงานของรัตเทอร์ฟอร์ดแอนด์รัตเทอร์ฟอร์ดโอเคป่ะคุณรู้ไหมว่าโบเขามีพี่น้องกับพี่อีกคนหนึ่งด้วยนะตอนสมัยแต่พี่ยังไม่ดังเพราะว่าไม่ได้คิดอะไรที่แบบสำคัญก็มีโบผมจำชื่อหน้าของพี่เขาไม่ได้แล้วแต่ว่านามสกุลเดียวกันเลยมีโบโอเคก็เหมือนกับอย่างเช่นว่าอะไรอย่างเช่นประเทศไทยกำลังประสบปัญหา PM อยู่เนี่ยคุณก็อ่านข่าวคุณก็ได้รับข่าวภาคเหนือคุณก็สมมุติว่าภาคกลางผลิตอะไรได้สักอย่างสารเคมีอะไรได้ซึ่งมันสามารถดูดซับคุณได้คุณก็เอา2ปัญหาเนี่ยมารวมกันแล้วไปจัดการปัญหาภาคเหนือแล้วคุณก็ดังขึ้นมาเหมือนกับมีโบเขาก็อ่านงานซึ่งมันเป็นบทความของพวก3, 4, 5คนเนี้ยแล้วก็ไปรวมกับงานเก่าพวกมักซ์ พลางก์แล้วเขาก็คิดทฤษฎีของเขาขึ้นมาก็ยอมรับก็ดังระเบิดมันก็เหมือนกันแต่ว่าเขาคิดแบบทฤษฎีของฟิสิกส์ประเทศไทยแนวอะไรบ้างประเทศไทย PM โครงประสาทประมาณนั้นนะครับประมาณนั้นเก่งมากก็คงไม่น่าเกินความสามารถของคุณได้นะคุณก็เห็นแนววิธีโบเขาสร้างทฤษฎีขึ้นมาแล้วครับคุณก็ทำได้ไม่ยากหรอกเราไม่ได้เกิดมาแล้วคิดทฤษฎีเองขึ้นมาแบบเดี่ยวๆเราแค่สังเกตคนอื่นด้วยแล้วก็พยายามหลอมรวมเชื่อมให้มันเป็นยอมรับได้โอเคif you see in a different way there is another series which is called food series. Okay, it's observed at n equal to 5. I'm not sure whether is there anyone who already investigated the orbit n equal to 6. If not, you may be the guy who get the title for that orbit. นะไม่แน่เขาจะเรียกซีรีส์ของคุณก็ได้นะถ้าn เท่ากับ 6ยังไม่มีใครจัดการนะคุณก็แบบมันมีคนทำนะผมไม่น่านั่นแหละไม่น่ารู้เหลือให้เราแล้วเพราะว่ามันรอดมาตั้งแต่คุณปู่แล้ว2 generation ไม่เหลืออะไรให้เราเท่าไหร่นะครับคุณ6มีใครทำคุณทำปุ๊บเขาเอานามสกุลคุณทันที เห็นป่ะซีรีส์ของคุณเลยอนุกรมของคุณนะครับแต่ว่าเสร็จไปแล้วไม่เหลือให้เราแล้วก็สิ่งที่มันยากก็คือถึง12เลยเหรอเนี่ยเอาไปกินหมดแล้วโอเคไหมครับไม่เหลือให้เราแล้วคุณก็ไปเล่น13 18อะไรก็ว่ากันไปครับโอเคอ่ะคุณก็ไปทำธาตุอื่นที่มันใหญ่กว่าไฮโดรเจนไปนะครับเพื่อว่ามันจะได้ยอมรับคนเอาเงินเอาทองมาเป็นรางวัลให้คุณได้ครับเห็นไหมthat's those are several theories that have the same idea. Okay, both try to conceptualize the result from these 4 or 5 principles and he create the idea about his atomic model. Okay, this is shown in circular form. Okay, Lyman ultraviolet from any orbit to the first orbit. Barmer, which belongs to the visible region to human eyes, start from any orbit and fall down to n equal to 2, the second orbit. Other than this, you're gonna sorry, photon, whether it's Paschen series, bucket series, or Flume series.
อันนี้คือเป็นเลนส์ที่ทำให้อิเล็กตรอนลงมาที่ชั้นต่างๆได้
ก็คือเขาศึกษาในธรรมชาตินะครับว่าถ้าอิเล็กตรอนมันกระโดดลงมาจากเชลล์ต่างๆมาที่ออร์บิทเช่น3อย่างเงี้ยคนเนี้ยเขาสังเกตมาผมไม่รู้เขาใช้เครื่องมือวัดอะไรอ่ะวัดแสงอินฟราเรดแบบเนี้ยมีคนทำหมดแล้วผมไม่เหลือให้คุณแล้วคุณปูไม่เหลือช่องว่างให้คุณเกิดแล้วอ่ะคนโลกของฟิสิกส์อ่ะโอเคปะคุณปูเอาไปกินหมดแล้วอ่ะเห็นปะคุณก็ไปเล่นธาตุอื่นอ่ะที่มันใหญ่ๆหน่อยนะเพราะว่านี่ยุคบุกเบิกอ่ะโอเคปะแล้วก็ปัญหาคือคุณจะเอาเงินมาจากไหนที่จะดีเทคพวกอินฟราเรดรีเจียนอย่างเงี้ยที่มันแบบว่าอันนี้มัน energy มันต่ำใช่ป่ะ energy ต่ำมันก็จะต้องแลมด้าสูงอ่ะคุณไปหาเครื่องมือที่มันดีเทคแลมด้ายาวๆได้คุณอาจจะเกิดซีเรียลของคุณแล้วคุณก็ส่งงานไปใช่ไหมเห็นไหมส่งพวก journal หรือ paper วารสารฟิสิกส์เดี๋ยวคุณก็ได้ชื่อกันหรือเขารอคุณเสียชีวิตแล้วเขาก็จะถึงยอมใช้นามสกุลคุณนะเห็นไหมโอเคthis is the study of the process that the process where electron fall down to certain orbit. Right? Barmer series is the one that is quite important to our daily life because the product or the outcome from the Barmer series can be observed by human eyes. We are going to study the Barmer series in this example. The electrons can start from any orbit, from any shell, and they are going to fall down to the second orbit in equal to 2. And the result will appear as the light that can be seen by our human eyes. Of course, the second orbit is not the lowest one, which is minus 13.6, but it's only negative 3.4 eV. Okay. The question is, what is the longest wavelength in the Barmer series? And try find the frequency and the energy that level and shortest wavelength in the Barmer series. You need to know that, as I always mention, the light that has higher frequency would have more energy, right? It means that that light would have short wavelength, right? Short wavelength implies high frequency and also high energy. Okay,
you need to use that idea to solve these two problems. Longest wavelength means you have low frequency and also low energy, right? You're gonna need to look at the orbits in the boundary. Which one has the shortest distance of the falling down process?
ก็จะสองสามหรือสอง
It's 3 to 2, right? This route will give you the least amount of the energy. The least energy means you get the longest wavelength. And which route will provide you the highest amount of energy? Of course, you should start from the longest line. You need to start from infinity line, right? To the second line here. That's the longest arrow that you can find in the boundary. The highest amount of energy would imply shortest wavelength or higher frequency, right? So you get the idea from that. And let's compute the longest wavelength, which corresponds to the shortest, the smallest frequency. In the power series, you have you can use the Rydberg formula. You flip lambda to be the numerator. You use the max idea and a kind of optimization in battery. You can find that n item that you can start the provider maximum wavelength will be number 3. You start from 3 and you jump, your electron jumps to second orbit. Okay. And the maximum will be 656 nanometers. And you can see that 656 would correspond to the region that we can observe by our human eyes, right? 656 NM. Light. What color is that? 656. You're gonna see, yeah, it's around orange, between orange and red, right? That lies in the visible region to human eyes. Okay, 656. And lambda min, that corresponds to the highest amount of energy. You start from infinity line to the second line, right? F min, F min corresponds to the lambda max, okay, the longest wavelength. We get 4.5 into 14 hertz, which is very high. And the energy of the photon is 1.88 eV. Okay. 1.88 because you can see that the difference between 151.3.4 is around 1.88. Okay, and that's why we get the energy difference on this level. And regarding the shortest wavelength, which corresponds to the highest amount of energy or highest frequency, it means you need to start from infinity. Okay, after you use the maximization calculation, it means your initial state should be the maximum point, the infinite point. Once you use infinity, in equal to infinity, so this one will be 1, okay, approximately 1. Get 4 by RH, which is the Rydberg constant, and you get 364. You can see that this wavelength is shorter than 656. Shorter wavelengths means you get higher frequency, you get more energy. What color does 364 nanometer correspond to? 364, right? 364 NM. Huh? Oh, 364 364. Oh my god. 364 mm light. ทำไมไม่ขึ้นแล้วใช่ป่ะมันมองไม่เห็นแล้วใช่ป่ะ Okay, it's ultraviolet. I don't know when. 364 is around here. It's UV already, light in UV, ultraviolet. We cannot search by eye. Okay, brown can cover the case when our human eye can not detect light. Okay, apart from the electronegativity, there is another quality that might be useful for us. ผมก็ไม่รู้ว่ารู้ขนาดอะตอมแล้วเกิดประโยชน์บ้างแล้วเราทราบขนาดอะตอมแล้วเกิดประโยชน์ไหมครับมันก็น่าจะเกิดประโยชน์อยู่นะเพราะว่าทุกวันนี้ทรานซิสเตอร์เราไล่ไปถึงขนาดของไซส์ของอะตอมนะครับทรานซิสเตอร์ทุกวันนี้ได้เท่าไหร่นาโนมิเตอร์ป่ะนาโนครับแต่ว่าไซส์ของอะตอมมันอยู่ที่อะไร 10 to negative 10 it's angstrom. Okay, nano is 10 to negative 9, so very close right now. Okay, ต่อไปนี้เราจะโปรเซสทรานซิสเตอร์แบบหลักแบบอะตอมแล้วครับเห็นไหมไปมากกว่านี้มากกว่านี้คุณต้องเล่นแถวพวกควาร์กแล้วเดี๋ยวอยู่ท้ายๆของบทยังลึกๆอ่ะเดี๋ยวคุณไปเล่นพวกควาร์กแล้วคุณจะดีไซน์วงจรไปทางไฟฟ้าทรานซิสเตอร์โดยเล่นที่ควาร์กแล้วทีเนี้ยนะครับรุ่นคุณครูเขายังเล่นพวก10 กำลังลบ 6ไมโครเมตรอะไรกันอยู่อ่ะมารุ่นปัจจุบันรุ่นโปรเฟสเซอร์ผมนะที่สอนผมอยู่ที่เยอรมันนาโนมิเตอร์ผมว่ารุ่นถัดไปจากคุณอ่ะเล่นพวกควาร์กแน่นอนไส้ในของพวกโปรตอนแล้วโอเคit's the radius of atom โอเคหน้าของทุกสิ่งทุกอย่าง engineering นะครับมาจากทรายนะวิทยาศาสตร์คือฟิสิกส์นี่แหละวิศวกรนะครับก็คือคนที่ประยุกต์วิทยาศาสตร์มาใช้ให้ชีวิตมนุษย์อยู่สุขสบายครับ Okay, the radius of the atom can be found from this expression and once you substitute everything to the constant to this one, you can turn out with this formula 0.05293. X squared unit is in nanometer. Okay, you can do 0.5 to around 0.5 angstrom. And we still leave the dependence on the quantum state. Okay, the number 8, which is only is the power 2 of the quantum state. It means that if your n is larger and larger, your atomic size is going to be also greater and greater, bigger and bigger. And one thing you need to know is atomic mass unit. This one is important in the next chapter also, right? It's 112. You may find several elements in the order, but the most common element that can be seen in everyday life is wood. Okay.
ให้ติดที่ไหนอ่ะ
Okay. What you can see is the carbon 12, which is the most stable version of the element that you can observe by eye. Like you have here wood. Okay, wood contains carbon 12. Okay, so here is the carbon element that you can observe by in daily life. Carbon 12. We don't depend on carbon 14 because carbon 14 is not stable. It's an isotope to our life. Okay.
Yes sir. Yes sir.
So it's 1/12, 1/12 of the mass of come. Wait, that's atomic.ได้แล้วครับเรียนได้เรียนแน่นอนครับมีที่เรียนแน่นอนครับเป็นสาขาแล้วของคุณแนวแพทย์ไม่ใช่เหรอแนวแพทย์แพทย์ไม่ได้ยืนคุณขอrecommendation แพทย์เป็นอุตรุดเลยอ่ะไล่ทุกมหาลัยเมืองไทยเลยมั้งเกือบหมดแล้วอันนี้มีที่ไปแล้วนะครับแจ๋วเลยคุณอมคาถาอะไรไปพูดกับเขาตอนสัมภาษณ์เขาyes sir คุณเขาสัมภาษณ์คุณเป็นภาษาอังกฤษหรืออะไรอังกฤษอย่างเดียวไม่รู้ yes sir okay but okay, let's consider the fundamental subatomic particles. It's not elementary, but it's only fundamental because we are at the chapter of atomic model. So we are going to pay attention to major components related to atom only, and those are neutron, proton, electron. Right? There are several features that we need to talk about. The first one is the symbol. Okay, the first thing. If you go higher, the next layer, they're going to follow this symbol in simple way, individual expression. They're going to use n to the power of 0. The next one is p with a superscript of plus. We use plus because proton has the positive charge. Another one is electron. Simply use E as electron and with the power of negative side on the superscript. Because electron has a negative charge, and if we follow the atomic symbol, it's going to be N, which is the name of neutron. The left superscript represents the number of nucleons. Because we have only one nucleon, which is neutron itself, and the lower left subscript is the position or the number of protons. Because neutron is neutron, it's not proton. We don't have proton, so that's why this number is zero. Okay. Let's talk about proton. Proton is one of the nucleon. So we count it as number one. Proton is one. And proton can be seen as one. And because proton, which is important, it changes the elements, right? Because we count the number of protons as next element. We differentiate several elements from by using the number of protons. So we will say number one here, one proton. All right. And the next one is E minus. Electron doesn't belong to nucleon at all. Nucleon is composed of neutron or proton. So there is no nucleon. Okay. Regarding the number of protons, this is not proton. It's opposite to the proton, so it doesn't have positive charge, but rather negative one. So that's why we have to say minus one as the lower left the subscript, left subscript here, minus one. And where can we find neutron? Neutron, of course, could be found in the nucleus. Proton can be found also in the nucleus, but not electron. Electron moves around the nucleus. It's called orbit. Okay, that's what the level, energy level that we have studied before, and we can also even the size of the atom, right? Let's talk about mass, which is quite important in physics. On the scale of SI, everything is measured with respect to 10 to the negative 27 kilograms. Neutron has 1.67 also for proton, but neutron is a little bit heavier, and it has more mass, 4.9, than 2.6 in proton. Electron cannot be written in the order 27, but rather even smaller, okay, 10 to negative 31. 9.1, okay, is around 10,000 light years than proton and neutron. Let's talk about the mass relation with respect to the electron. Neutron has more mass than proton by 6, okay, 1,842 836. Let's talk about the mass in atomic mass unit. We're gonna use it when we arrive at the chapter 7, the next chapter, which is atomic physics. It's 1.008. This is 1.007. And the mass of electron is even smaller than that, much smaller than proton and neutron in the scale of atomic mass unit. And when we talk about I forget the word. What is that? The combined energy or something. Okay. We are going to use the E equal to mc squared. That's the expression by Albert Einstein, EMC. And the energy for the nucleus is not in the EV scale like in the chapter, but rather in mega, million times greater than the energy in electron scale. It's 939, 938, and this one is much less than that, it's 0.511. Let's talk about the charge. The charge for neutron is 6 because neutron is neutral. Okay, it doesn't have positive behavior, it doesn't have negative behavior. Okay, it doesn't have any attractive effect to any charge, so it's neutral. But if you go into the detail, the charge of the proton, the neutron can be computed from something that stays inside the neutron, and that's called up quark and down quark. Neutron has single up quark and 2 down quarks. 1 up quark corresponds to 2/3. 1 down quark corresponds to minus 1/3. Because you have 2 down quarks, 2/3 plus 2 minus 1/3, you're going to get 0 from this expression. And that's the reason why neutron doesn't have any charge. Neutron stay neutral. And proton has 2 up quarks and 1 down quark. 2 up quarks means you have 2/3. 1 down quark means you have 1 negative 1/3. And then you're gonna get the combination like this, and you end up with number 1. So that's why proton has exactly 1 positive charge, and neutron has negative 1. Okay. Regarding the spin number is the momentum behavior of each particle. Is 1/2. Okay. If you want to know the detail, what is the spin? Spin is the coefficient in front of the Planck constant. Okay, when you are talking about the momentum, you're gonna get 1/2 in front of h, and that's called spin factor. It's in front of Planck constant. It's the reduced Planck constant h slash 1.05 cm. Okay. The number of protons in the atom is unique. It's the element. The number of protons in the nucleus of atom is equal to the atomic number. It's usually known as little set. Okay. In the neutron atom, of course, you may know earlier the number of protons should be equal to the number of electrons, right? ทั้งหมดนะมันแบบผมไม่รู้เกิดอะไรขึ้นเป็นฝั่ง the number of neutrons the mass number, which is denoted by capital F, is the number of protons and number of neutrons. This is the number of nucleon actually. If you want to determine the number of neutrons, you just subtract the number of nucleons by the atomic number. That's the number of protons. You get the number of neutrons. Okay, the hydrogen-like atom means the atom that has a single electron. Whether it's in the neutral state or equilibrium state or it's in ionized state, will occupy only one electron. Okay, we're gonna see some more detail about this later. And when an atom has atomic number as set, whether it's 1, 2, 3, 4, 5, the term E square can be replaced by set E square. Now we're gonna extend the concept of Bohr model to the bigger atom. Okay, not only hydrogen. We're gonna see the bigger atom. นะคุณปู่ก็ไม่เหลืออะไรให้คุณเล่นแล้วเพราะว่าคุณปู่ก็ซัดอะตอมที่ใหญ่ขึ้นกว่าไฮโดรเจนอ่ะผมก็ไม่รู้คุณจะเล่นอะไรแล้วทีนี้นะครับที่จะแบบว่ามีชื่อเสียงโด่งดังได้รับโนเบลไพรส์เพื่อตัวเซตคือจำนวนของโปรตอนที่อยู่ในนิวเคลียส C. Atom is called atomic number. Okay, this quantity is the fundamental stuff that you are going to see in the next chapter. It's the atomic number. Okay, Z or set is the number of protons. For Sem rule, if you want to use this expression to hydrogen, if you substitute set equal to 1, you get the same expression as we have had before, right? Minus 13.6 divided by 6. But if you have a bigger atom like what is the next element after hydrogen? Helium. Helium has 2 protons and 2 electrons. In that case, your set for helium is going to be number 2. So you need to substitute it to be number 2. But helium itself cannot be applied to this formula directly, straightforward. No, you have to throw away every electron out of the nucleus of helium, leaving as 1 electron. Okay? The electron should remain in the orbit of the helium by 1. Okay? In that case, you can apply this formula. What about the Lindbergh formula? You can still have the Lindbergh formula for a bigger version of the atom. Okay, by having Z squared or Z squared. Okay, and after that, the radius of the proatomic model can now be changed to the same thing, K2.05293 squared, but you need to have the division set. It's better for us if we consider a realistic case, like the next one after the hydrogen, and that's helium. Okay, helium is quite important because the more stable helium-42 is going to be alpha particle for us, right? If you throw away 2 electrons from the helium nucleus, helium 42, you're going to get an alpha particle, and that's dangerous for our human body. A singly ionized helium, it means usually helium has 2 electrons, right? But single electron is thrown away. Okay, you pull 1 electron out of the radius of helium. You still have 1 remaining electron in the orbit around the nucleus of the helium. It's denoted by He+1 because you lose 1 electron and it's going to be 1 positive dominant. You consider the orbit at n equals 1. Okay, the atom is in the ground state. Let's talk about the details. Of course, this is what you can realize. This is C, right? And atomic weight is atomic weight is different from the number of neutrons. Of course, in helium, you would have 2 neutrons and 2 protons. The number of neutrons will be exactly 4. Okay, but in realistic, you cannot get that value for the atomic weight. What you can observe is 4.002602 in the atomic mass unit. The next feature is electron configuration. You get 1s2, okay, because it's the first here. It S orbit. Name is helium. And you get this symbol which means hexagonal crystal. Hexagonal. 6 เหลี่ยมครับ6เหลี่ยมนะ 1 2 3 4 5 6 6 sides. And you get the dot symbol. Dot symbol means it's invisible by eye. It's in gas phase. Okay. At the room temperature 20 degrees Celsius, no one can see helium by eye because helium remains in the gas phase. Okay. The atomic weight, which is Ar. Helium 2 is 4. And atomic number is equal to this number. Okay. And find the energy in the ground state in electron volts for the helium that lost 1 electron, and the radius of that helium which lost 1 electron. Of course, that equal to 2 for helium and n equal to 1 for the ground state of helium. You substitute it into this expression that equal to 2 n equal to 1. You get minus 54.4, which is even lower than negative 13.6. Okay, minus 54 is even lower. And the radius, you can see the radius is this is n square, right? N equal to 1. Radius is smaller, okay, because you have number 2 divided as a division and you get 0.26465 micrometer. Okay, the size is smaller, and now we move to the next one. Okay, is the doubly ionized lithium. You know, lithium has 3 electrons and 3 protons in the equilibrium state, stable state. Lithium has something different from helium because the atomic mass, atomic weight, cannot be known precisely. Okay, they can't find the value in this region from 6.938 to 6.990. Lithium has 3 protons and 4 neutrons, right? So from what we understand, we should get the atomic mass as 4 plus 3, which should be 7, right? But it's not the case. It's very close to 7, 6.997 or 6.93. Because there are some interaction between neutrons and protons to get binding energy. Okay. is used with Li, which stands for lithium. The electron configuration is 2s1 because you reach the one that's beyond 1s2. Yeah, this 2s1. And you get the dot symbol. It's strongly basic. It's acid-based property, higher valence of time. So lithium has an easy interaction or activity to other stuff, other elements. So it is good if you have lithium battery, like in your mobile phone, in your electrical vehicle. It's not good. If lithium gets leaked from your battery, it can be full to your body because lithium can make the oxidation to anything. And it has the acid property. Is it good to have acid close to your skin? No, right? Okay, so lithium is not quite safe. Huh? Acid ครับเป็นเบสใช่ป่ะเขาบอกเป็น acid base property มันเป็นเบสใช่ป่ะไม่ใช่คือstrongly basic เป็นโลหะอัคคาล so
มันบอกว่าไอ้ที่มันวายให้คือมันเป็นบอกว่ามันมีสองเป็นค่าอะไรเขาบอกแค่ว่าไอ้ตรงนี้มันบอกว่าเป็นเบสว่ามันบอกว่าไอ้ภาษา
เป็น acid so it's alkaline metal due to the yellow color. So and the shape is in crystal structure and it stays in solid phase. So lithium is in solid phase during at our temperature. But you know that I'm from the Department of Electrical Engineering. Lithium is not so stable. It's vulnerable. It's harmful to our human life. And so nowadays we try to develop a new kind of battery that uses sodium. Okay, sodium. Where is sodium? You can look. It lies in the same group as lithium. Decayable. Okay, where is sodium? You can see here, right here. Lithium, sodium is right here. It's a bigger version of lithium, but it lies in the same group, same column as lithium. So, sodium would be able to resemble the property of lithium, but is bigger, it's not close to chemical activity like lithium. And it's not rare metal, right? So sodium would be easier to find on Earth. The price should be cheaper. Okay? When you deal with something in engineering, we don't talk about the scientific property only, but we need to deal with the cost in economic sense. Okay? It should be easy to find. It should have low price, and that would be fine to apply and use it with humans. Okay, this is lithium, solid in the room temperature. We're going to consider the first excited stage behavior of the lithium. What is the first energy, the first excited stage to lithium? ถ้าเป็นรุ่นพี่คุณคงจะให้ทำกันบ้านนะก็คือคุณจะไปเลือกธาตุที่สูงกว่าลิเธียมขึ้นมาแต่ว่ามันไม่ต้องทำกันบ้านแล้วคุณก็ไม่ต้องเลือกธาตุแต่ก็ใช้คอนเซ็ปต์นี้นะเห็นไหมfor lithium in the first excited state N equal to 2 and lithium needs to use set equal to 3, right? It has 3 protons. So 13.6 and z squared, that's equal to 3, right? 3 squared. Divided by the number of the index of orbit that you want to observe, so n equal to in this location. And after the division, you're going to get minus 30.6. Before you have minus 54 for here. This one is minus 30, is 30 higher. And the radius is 0.07. It will be bigger in the second order. Anyway, both theories give us the great idea in atomic model, right? But it was not the final stage of the atomic model. It was developed further as quantum mechanics. We're going to go further. Before we go to quantum mechanics, let's talk about this table, because this will explain many things in physics. You know, in chemistry, you need to know this table, which is periodic table, right? This is the big scale for us in physics, because we talk about the number of protons in each element. But for us in physics, we are talking about this table, which has finer behavior than one or single dot. Okay, this table contains mainly two groups. You see the violet and the green one, right, on the left. And this group is called fermion. Okay? We're going to use this word all the time, fermion. Fermion comes from the word Fermi. Fermi is the surname of Enrico Fermi, which is the Italian notable physicist. Okay. And on the right side, which is not the major thing, but it's also important, it's called boson, with this word, boson. Boson comes from Bose. Is the surname of an Indian physicist. Okay, we're going to see what is Bose. You know Fermi, right? Enrico Fermi. This guy. Enrico Fermi, he is the Italian physicist. He made something very good. The unit Fermi 10 to negative 15 is the distance you're going to see in the next chapter. Is derived from his surname, Enrico Fermi. And Bose, Indian guy. Okay, this is I don't know, Satyendra Nath Bose. Okay, this is Indian physics. He studied in India, and he tried to work in physics in India, and he made a great work, but he tried to submit his work about the theory to explain the location or the behavior of some particle on the right side of that table. And สิ่งที่ผมสอนเนี่ยมันจะเกินเนื้อหาของฟิสิกส์ชั้นม.ปลายแล้วนะมันจะทะลุลึกเข้าไปถึงชั้นปริญญาตรีปริญญาโทแล้วก็ผมก็ไปเรื่อยนะไปเรื่อยๆครับมันจะไม่มีในฟิสิกส์ม.ปลายครับแต่ก็จะให้คุณรู้จักและคุณจักทั้งหมดของในบทถัดไปด้วยโอเคThis guy discovered some theory about the behavior or the statistics of the particles on the right side in that table. And he submitted his work to the well-known physics journal, and it was not accepted. But he sent a letter to Albert Einstein. And Albert Einstein is a guy who is big impact in that journal, in that German physics journal. But Einstein really can see that his field is very important. So both change the paper and includes Albert Einstein here as one of the authors, and they submit the paper to that journal again. And what we expect? That work was accepted in the physics journal, and Albert Einstein invited him from India to stay with him in Germany to work with, together in a physics project. Okay. Yeah, let's get back to our table. This is the part of boson, this is the part of fermion. In fermion, we can divide the particles into two parts. The first one is called quarks. Okay, quark is the major, quark is the mass stuff to everything. One of two of major things that you realize in science is are protons and neutrons, right? สมัยผมเรียนฟิสิกส์ม.ปลายอาจารย์ไม่ผ่านลงลึกถึงขนาดนี้นะครับ เนื้อหาพวกนี้มนุษย์มันคิดขึ้นได้ประมาณ 20-30 ปีภายหลังนะครับ อันนี้เป็นสิ่งที่เจอมาเมื่อไม่เร็วๆนี้นะครับใช่ไหมแล้วคุณต้องขอบคุณพวกแลบอย่างเซอร์นะที่อยู่ประเทศสวิตเซอร์แลนด์นะครับผมพูดเรื่องนี้แล้วมีรุ่นพี่คุณนะคุณตกหลุมรักฟิสิกส์นะครับแล้วไปเรียนฟิสิกส์เลยไม่เรียนวิศวะไม่เรียนหมอเลยมีจริงรุ่นแรกๆที่ผมสอนนะครับเห็นไหมคุณน่าจะเป็นหนึ่งในนั้นก็ได้นะเพราะว่ามันยังไปต่ออยู่นะครับยังไม่จบนะมันยังมีอีกหลายปาร์ติเคิลที่เขาคิดว่าจะมีแต่ว่าอยากทดลองแล้วไม่เจอนะครับโอเค and okay the violet one is called quark group. The green one is called lepton. Quark represents the mass. Okay, it's formed up as the basic thing. What you can find not easily is up quark and down quark. And the big version are called sharp quark or top quark. Okay. And regarding the down quark, you get the big version like straight quark and bottom quark. ฮะ1 2 3ก็คือมันใหญ่ขึ้นก็คืออันเนี้ยคุณยังพอหาได้ในธรรมชาติบ้างแต่อันเนี้ยคุณไม่มีสิทธิ์หาได้ใช่คุณเร่งอนุภาคให้มันชนให้มีพลังงานจนเยอะๆแล้วชนกันมันจะได้ของที่มีมวลใหญ่อย่างนี้เดี๋ยวผมบอกให้ดูว่ามวลใหญ่ยังไง Let's talk about the mass. Mass of up quark that could be found is on the order of 2.2 mega electron volt. This is also 4.7. You can see that sharp quark is made from up quark. When you accelerate this one with a bigger energy, you're gonna get a bigger mass like 1.28 giga. Giga means 10 to 9, right? Mega is 10 with the power 6. And this one is even bigger than 1. It's 170. But those quarks, those big quarks are not stable. It's going to stay only in 1 by giga, 1 nanosecond. Okay, it's not stable. Also, up quark and down quark. Up quark and down quark cannot stay alone. They're gonna combine with each other to form up like proton and neutron. Okay. Okay. This is the big version. They cannot live in the real life, but humans use the particle accelerator. Let's talk about particle accelerator that is going on in research. they use electric field and magnetic field. Okay, in order to accelerate the particle in the long distance, 30 kilometers, 10 kilometers, when they have higher and higher speed, they would have also higher energy. Okay, it's made under the ground. It was built under the ground because this cannot be destroyed from human easily. Okay, and they use the electric field and magnetic field to accelerate the tiny particle. If you get the longer distance, you can have more chance to get higher energy, and you can see something, discover something new. You need to study well and apply for a job at CERN. Okay, CERN in the border between France and Switzerland. นะครับ เรียนฟิสิกส์ล้วนนะครับ แล้วก็ไปสมัครงานที่เซิร์นนะครับ ผมออกว่าเซิร์นนะครับออกว่าแซนก็ได้ครับออกเสียงเยอรมันจะออกว่าแซนครับที่เซิร์นนะครับ เรียนให้เก่งนะ แล้วไปสมัครงานที่เซิร์นคุณจะได้เป็นหนึ่งในนั้นครับ คุณจะได้เป็นหนึ่งในนั้นที่คุณอาจจะเป็นผู้โชคดีนะที่คิดพาร์ติเคิลขึ้นมาใหม่ คุณไม่ต้องสร้างบ้านเอาเงินตัวเองที่สร้างบ้านแล้วมาทำแอคเซเลเตอร์นะคุณสมัครไปทำงานที่นั่นแล้วพอคุณคิดพาร์ติเคิลได้เขาจะเอาชื่อคุณทันทีเช่นผมชื่อเท้าสีสกุลนะเขาอาจจะเรียกว่าเท้าทีสควอนก็ได้นะมันจะลงออนเสมอคุณเห็นไหมโบเซอร์มันก็เป็นอะไรโบซอนแฟมี่ก็ยังเป็นออนได้นะเขาจะเติมออนเสมอเลยยุคนี้นะแล้วคุณเรียนงานเป็นคุณครูเลยคุณเรียนฟิสิกส์ให้เก่งถ้าเรียนหมอไม่ได้เรียนวิศวะไม่ได้ต้องเรียนฟิสิกส์แล้วสายพาร์ติเคิลเลยนะไปสมัครงานที่นี่นะครับนามสกุลคุณมีสิทธิ์ที่จะเป็นหนึ่งในพาร์ติเคิลที่มันจะกำเนิดบนโลกนี้ครับเห็นไหมถ้าอยากเป็นนะก็คนเก่งๆบนโลกแข่งแย่งกันไปหมดเห็นไหมคุณก็ไปสู้กับเขาเห็นไหมผมพูดอย่างนี้เนี่ยนะถึงบทเนี้ยมีรุ่นพี่คุณสมัครเรียนฟิสิกส์จริงๆไม่เรียนแพทย์ไม่เรียนวิศวะตามแบบนั้นแล้วตั้งที่เขาตั้งใจนะหลงไหลไปเรื่องนี้เลยนะเห็นไหมโอเคnow let's get back to our table okay let's get into the detail หมดเวลาOh, sorry. We will talk about that later in the next lecture on Wednesday. See you. Bye bye. ครับ สวัสดีครับ